This is another video in our series for reciprocal frame vectors. We've been talking about curvilinear coordinates and reciprocal frame vectors. Just a reminder that suppose we have a surface where we have two parameter surface, so x is x of AB, then we would define our curvilinear vectors on that surface as the differentials of our position vector x with respect to the parameters a and b. We can then define coordinates with respect to our curvilinear basis vectors as y upper I, x lower I, or y lower I, x upper I, where the x lower i's are the xa, xb, xc, and so forth, the differentials with respect to our parameters, and the x upper i's are our reciprocal frame vectors. Our reciprocal frame vectors, so xa, xb, xc, so forth, all within the span of our original tangent space. So our tangent space is this plane formed by the xa, xb, or the higher dimensional analogs of that. Our reciprocal frame vectors are these vectors that lie within the span such that the x upper I dotted with x lower j for all ij and a, b, c, d, so forth are delta ij. And we found a geometric algebra form for this, for the reciprocal frame vectors, where we take the wedge product of xa, xb, xc all the way to our however many parameters we have, and then we take the wedge product of the same, leaving out the xi that we're interested in, and then we dot those two together, changing the sign for each time we have to move down the line. So that was our geometric algebra form for the reciprocal frame vectors. We found this in the 2D case just by solving the linear system that's specified by this span plus generalized orthonormality constraint, and then showed how we can generalize it like so, and why that works due to the geometric algebra distribution law of where we take a dot product of in this case, an m-1 blade with an m blade. What we're going to do in this video is we're going to just work through some examples with different parameterizations. So let's start. I guess the simplest parameterization that we can think of would just be x is x e1 plus y e2 plus z e3. So we should expect, and in this case, we have xx is e1, xy is e2, and xz is e3, taking our differentials. So we expect that xi equals xi equals ei. So let's verify that that's the case. So our volume element for all of our coordinate vectors in this basis. So we have xx wedge xy wedge xz is just e1 wedged with e2 wedged with e3, which is nothing more than the product e1, e2, e3. Since these are all orthogonal, we can drop the wedges. And similarly, so now let's compute what is e1, or x as we've been calling it. So that is going to be e2 wedged with e3 dotted with 1 over e1 wedged with e2 wedged with e3, which we've just found is 1 over e1, e2, e3. And again, dropping wedges, we have e2, e3 dotted with e1, e2, e3 divided by e1, e2, e3, all squared. So there, I just explicitly compute the inverse. So the inverse of any pseudoscalar is just the pseudoscalar divided by that pseudoscalar squared, and Now, if we go and compute this, we have, first off, E1 times E2 times E3 is just minus 1. Let's say minus 1. And this dot product is just going to be the grade 1 selection of the product of these, and that will be a vector. There will be no other grades, so we can just write this as a straight product. So that is going to be E2, E3 times E1 times E2 times E3. Now, if we want to, we could take E1 out to the end by permuting twice. And each time we do a permutation, we're going to pick up a minus 1 sign. So we have two minus 1s. So we stay with minus E2 times E3 times E2 times E3 times E1. And now group our E2, E3s. So we have a E2, E3 times E2, E3, which is minus 1. Our minus is obliterated, and we're left with, no surprise, E1. You can go off and show the same thing for E2 and E3, but in the end, what we're going to find is that, well, so what we have are x equals E1, xy equals E2, and xz equals E3, and we find that x equals E1, and xy equals E2, and xz equals E3. Not a surprise. That's exactly what we expected to find, but if we try this for the absolute simplest case, we should get the same answers. Another very simple case that we can do is, let's take a space-time surface in our Dirac algebra. So we have a basis of gamma naught, gamma 1, gamma 2, gamma 3. And let's pick a subset of that space. Let's say the gamma 2, gamma naught subspace. So a space-time plane with the y-axis and the time axis. So our position vector within that plane is going to be, let's say, we have t gamma naught plus y gamma 2. Our position vectors, or our what we would call the curvilinear vectors for the space. So xt is just going to be gamma naught, and x sub y is going to be gamma 2. And we want to find now what is xt and xy. Well, we know what the answers are. It's gamma naught and gamma 2. But we should be able to show that this is the case. And let's do that. So if we wedge our pseudoscalar elements together, we get gamma naught wedged with gamma 2, which is just gamma naught times gamma 2. So now we can go and compute xt. xt is just going to be xy dotted with 1 over xt wedged with xy. And I've mixed up my indices here. We should have a downstairs index. We don't know what x upper y is yet, but that's what we want to compute. And xy is just gamma 2, and we have 1 over gamma naught gamma 2. We do this inverse explicitly. We now have gamma 2, not gamma 2 divided by gamma naught gamma 2 squared. And even though this is bivector squared, the space-time bivectors have a positive square. So we can see that if we multiply this out, gamma naught, gamma 2, gamma naught, gamma 2, which is minus gamma 2, gamma naught. I'm flipping the order of this first pair and changing the sign, times gamma naught, gamma 2, and gamma naught times gamma naught is 1. So we have minus gamma 2 times gamma 2, and gamma 2 times gamma 2 is minus 1, so we end up with plus 1. So this here, our xt, is gamma 2 times plus 1 gamma naught, gamma 2, and flipping the order of a pair of these, let's say we get gamma 2, gamma 2, gamma naught, minus. And gamma 2 times gamma 2 is minus 1. We have minus minus 1, so this gives us gamma naught. So we have xt is gamma naught, which is xt. That's what we expect. Now we have, let's do our xy. So our xy is going to be minus xt over xt wedged with xy. And we've already found this, so we have minus, not gamma 2, but gamma naught, dotted with gamma naught and gamma 2, which is just the product of these. And gamma naught times gamma naught is plus 1, so we have minus gamma 2. And now this gives us, we have successfully computed that xt is xt equals gamma naught, and xy equals minus gamma 2, which is minus xy. Sure enough, if we go back and we compute some arbitrary vector now, so if we have y equals, let's say y naught x naught plus y2 x2, and mixing up symbols, so that's xt xy, then we would find that y naught is y dotted with gamma 1, and y2 is y dotted with, that's gamma naught and gamma 2. So this works in the simplest cases in both Euclidean and non-Euclidean spaces. Now let's move on to some more interesting parameterizations now that we've proved the most trivial cases. And my mouse is gone. There it is. Okay. So let's do a circular parameterization. Say x is r e1 e to the I theta. So this is just a fancy way of writing e1 cos theta plus e2 sine theta, but we can compute our curvilinear coordinates with respect to this parameterization, this r theta parameterization, and we get e1 e to the I theta, and x theta is our e2 e to the I theta, since e1 times I is e1, e1, e2, which is e2. So these are our basis vectors. And we have here a unit vector, and we have r times the unit vector. So we expect that our reciprocal frame is just going to be 1 over this, which is itself, and our reciprocal frame vector for x upper theta is going to be 1 over this, which would be 1 over r. So basically theta hat divided by r. And let's verify that that's what we get. So first off, we have what is our volume element, or area element in this case. So xr wedged x theta, and we computed this in the previous video. but that is just going to be the grade 2 selection of e1 e to the I theta, r e2 e to the I theta. Take the grade 2 part, which is r times e1 e to the I theta, e to the minus I theta e2, since these satisfy a conjugate permutation relationship. We conjugate the complex exponential to when we flip sign, when we permute, and sure enough, those are killed. Our grade 2 selection is just left with the product of e1 times e2, so we have our e1 e2, or Ri. So 1 over xr wedged with x theta is 1 over Ri, which is minus I over r. So our x upper r, the first reciprocal frame vector, is just going to be x theta dotted with minus I over r. So that is x theta was r e2 e to the I theta, and we have minus e1 e2 over r. So our r's cancel, and we can, oh, and this, oh yeah, okay, we're good. I was confused for a sec when I saw the complex exponential here, thinking that we should have some sort of cancellation, but we don't actually, that isn't the case, and the reason is because we basically want that complex exponential. So if we permute e1 with e to the I theta, we get e1 times e to the minus I theta, but then if we do that again with e2, we get e2 times e to the now plus I theta, so we're left with e2 times e1 e2 e to the I theta, which is just minus that is plus e1 e to the I theta. And sure enough, we found xr. This is our r hat. That's all good. And how about x theta? So x theta is going to be minus xr dotted with minus I over r, which is minus e1 e to the I theta times minus e1 e2 and a 1 over r. And same deal, we can say minus 1 over r e1 e2 times e to the I theta. Oh, and sorry, there was a minus and a minus, and I've left a minus instead of canceling it out, which should be a plus, and we are left with 1 over r e2 e to the I theta, which sure enough is just theta hat over r, which is what we expected. That is our xr. So in this case, we have found that xr, which is r hat, is e1 e to the I theta equals x upper r, and x theta, theta hat r, is r e 2 e to the I theta, and x theta is 1 over theta hat, which was 1 over r u2 ubi theta. So we found all of that. So 1, 2. So this is also a somewhat simple case because we knew that this would be the result a priori because we had a set of orthogonal basis vectors. And so next step up in complexity is let's compute the reciprocal frame for something that is non-orthogonal. And a good example of that would just be an elliptical parameterization. So if it's say we have A and a semi-major axis of A epsilon, so B is A epsilon, and we take x is A, E1 cos theta plus A epsilon E2 sine theta. If we compute our XA, that is just E1 cos theta plus epsilon E2 sine theta, and our x theta is A times minus E1 sine theta plus epsilon E2 cos theta. Now we have a non-orthogonal basis. So one basis vector may be pointed that way, and then the other one here. So we have XA and X theta. They're going to be, these basis vectors would be perpendicular at the axis crossings, but nowhere else. So in general, we can go and compute use our formula for the reciprocal frame vectors for this non-orthogonal basis and see what we get. So first thing we need is the volume element, which is an area element in this case. Our hypervolume element is probably a better description, which reduces to an area element in this case. So we have XA wedge X theta, which is grade 2 selection of E1 cos theta plus epsilon E2 sine theta times, we take the A out, and we have minus E1 sine theta plus epsilon E2 cos theta. Select grade 2. So we do this selection here. We have E1 times E1, which will give a factor of 1. So we have minus 1 cos theta sine theta, but that has no grade 2 component, so we can ignore it. Then we have E2 times E2, so we have a plus epsilon squared sine theta cos theta term, which also has no grade 2. So only the cross terms generate grade 2 selections. So we can drop the grade 2 selections and just enumerate the cross terms. So we have here A times epsilon E1 E2 cos squared theta, and we have minus epsilon E2 E1 sine squared theta. So that is A epsilon E1 E2 times cos squared theta plus sine squared theta. And here I have used the freedom to rewrite E2 times E1 as minus E1 times E2. So the minus signs clobber, and we're left with a factor of 1 cos theta plus sine theta. So our area element is just A epsilon I. That's nice and simple. So XA wedge with X theta. And I'm going to leave a little bit of this still on the screen because here we have our, this is our XA, and this is our X theta divided by A. So just so we can refer to those. So our x upper A is going to be x theta dotted with 1 over A epsilon I. And we can drop our dot product and just write that as x theta divided by A epsilon times minus I, which is minus 1 over A epsilon. And I'm going to just do this in my head here. So E1 times I, or minus E1 times, I think it's worth writing it out. So we have, say, minus E1 times minus I is E1, E1, E2, which is E2. And we're going to have a 2 times minus I, which is E2 times E2, E1, which is E1. All right, so x upper A should be E2 sine theta plus E1 cos theta. And our x upper theta is going to be minus xa times minus I over A epsilon, which is minus, so xa, and this, there's a mistake here, there should be no A there, because there was a factor of A in x theta, and I dropped that in my inline evaluation. So x theta, we have plus 1 over plus A epsilon and xa times I. And so here, xa times I, so E1 I is E2, and E2 I is minus E1, so that we have E2 cos theta minus epsilon E1 sine theta. So we should be able to compute dot products here and see that we have zeros. I'm going to leave that as an exercise for the reader or for the viewer, and let's move on to a couple other cases. So I'm going to do another STA parameterization. So this is again using a Dirac basis. And I'm going to use a null vector parameterization of the space-time plane. So of a space-time plane. So I'm going to pick, say, gamma naught, gamma 1. Let's look at parameterizing the space inside the light cone, where this is gamma naught plus gamma 1, and this direction is gamma naught minus gamma 1. So we can easily form linear combinations within the light cone by saying x naught plus x1 and b x naught minus x1, or gamma e. So we have the interesting phenomena here of both of these vectors being null vectors, so they square to minus 1, or would square to 0. They're both on the light cone. And so it's clearly the reciprocal vectors are not going to be, they won't just be the inverses as they were for the circular case. So we have x of A is gamma naught plus gamma 1, x of B is gamma naught minus gamma 1, and our area element is gamma naught plus gamma 1 wedged with gamma naught minus gamma 1. And looking at these, any of the like terms are killed, and only the unlike terms are remain, and we see that we have 2 gamma 1 gamma naught remaining. And again, that is a space-like vector that squares to plus 1. So if we invert that, we have x upper A is x lower B times 1 over 2 gamma 1 gamma naught. So that xb is gamma naught minus gamma 1, and to have 1/2 gamma 1 gamma naught over gamma 1 gamma naught squared, which is 1. And we are left with half of gamma 1 times gamma 1 is minus 1, so we have minus minus 1, which is plus 1 times gamma naught, which is gamma naught. So half of gamma naught, and our next term is gamma naught times gamma 1 gamma naught, which is minus gamma naught squared gamma 1, which is minus gamma 1. Let's see if that works. So we should expect that xa dotted with xa is 1. And xa was gamma naught plus gamma 1. I'm going to dot that with half of gamma naught minus gamma 1. And so gamma naught squared is 1, and gamma 1 times gamma 1 is minus 1, so minus minus 2, and we get 1 as we expect. Good. All right. And we should also have that xa dotted with xb is 0. And in that case, we have gamma naught oh, and I did these backwards. I made 2 sign errors. This was xa, which is minus, and this is plus, but with the both of those sign errors, we get the same result. So anyways, gamma naught minus gamma 1, 1/2 dotted with xb, which is gamma naught minus gamma 1, which is 0. So this works. And we could go and compute the same thing for x upper b, and clearly we're going to get half of gamma naught plus gamma 1 in that case. So that can also be left as an exercise to the viewer. Let's now do one more case, relativistic case. So let's take instead of a circular parameterization, let's do hyperbolic parameterization. So let's take a gamma naught e to the, let's call it j alpha. And I'm going to write j here as gamma naught gamma 1. So our curvilinear bases are gamma naught e to the j alpha, which incidentally is just gamma naught cosh alpha plus j sinh alpha plus j, and that gamma naught j is gamma 1, so that's gamma naught cosh alpha plus gamma 1 sinh alpha. So this is our standard hyperbolic parameterization. If we were to draw it out, and we would have curves like so, all within the light cone. So hyperbole within the light cone. And like if I'm looking at a specific area element, it's going to be It's going to have like a hyperbolic structure, something like that. I think that the edges are actually going to be a bit different. It's going to look more like that. So in our parameter space, our area elements are going to be little pieces like that. Anyways, we can also compute our x theta, which is a gamma naught j, e to the j alpha, and it's not x theta, but x alpha. Alpha is our rapidity, and that is a gamma 1 e to the j alpha. Okay, so what's our area element? XA wedged with x alpha is grade 2 selection of a gamma naught e to the j alpha times gamma 1 e to the j alpha so that is a gamma naught e to the j alpha. I'm going to flip the order of here, changing the signs appropriately, and the sign change is e to the minus j alpha gamma 1, just like it was in the circular parameterization, and we're left with a gamma naught gamma 1 that we've seen. So now our XA is X alpha gamma naught gamma 1 divided by A, which is A gamma 1 e to the j alpha gamma naught gamma 1 divided by A, which is minus gamma naught e to the j alpha. And does that sign make sense? No. So I was trying in my head to do gamma 1 e to the j alpha gamma naught gamma 1, which is gamma 1 gamma naught gamma 1 e to the j alpha, which is minus gamma naught gamma 1 squared e to the j alpha, and gamma 1 squared is minus 1, so we have minus minus 1, which is plus 1, which is plus gamma naught. We should have plus here. All right. And then our x upper alpha is minus x a gamma 1 gamma naught over a, which is 1 over a gamma naught e to the j alpha gamma naught gamma 1, and that is gamma naught squared times gamma 1, so minus 1 over a gamma 1 e to the j alpha. All right, this is also good. And then if you could go off and compute the dot products, we should be able to find that. Let's do xa dotted with xa, which is just xa squared, which is 1. That's good. Xa dotted with x alpha is gamma naught e to the j alpha dotted with gamma 1 e to the j and there should be a vector of A in there. And again, that is just going to be the grade 0 selection of A, gamma naught, gamma 1, which is 0. Okay, and you could do it the same thing for the other pairs, and we should find that we have the reciprocal relationship that we require. Anyways, those are some worked examples where we compute the reciprocal frame vectors for a few different cases. And I think that is enough for this video.